So good evening, everyone. My name is Shamim Malhotra, and I'm a PhD scholar working in the field of partial differential equations at the Department of Maths of IIT in Delhi. So I'm the teaching assistant for this multivariate calculus course. So in this course, we would like to basically our continue a general analysis from one variable calculus to multivariate calculus, where the independent variables which we consider are now more than one here. So in this session, I will be discussing few questions. So without further ado, let's start our questions. So let me start with the session. So let's start with the question number one. So as of now, there's no participant, but let's start anyway. So firstly, I would like to discuss about, suppose I have a function given as fx, basically a function given as a function of three variables, which I'm giving as x plus 2y minus z whole divided by 2x plus y plus z. So I have this function of three variable, and what I want to do with this, I want to find the level surface of this function through the point the point being 1, 2, 1. So how we solve this? We basically to find the level surface. So we of a function at this point, we would just have to calculate what the value of our function at this particular point. So let's find the value for a function at this point. So I would like to find the value of a function at point 1, 2, 1. So it will be 1 plus it's 4 minus 1 whole divided by 2 plus 2 and plus 1. This will be 4 by 5. So I would like to calculate our basically the level surface when my function has equal to value 4 by 5. So anyhow, so let's. So what we like to do, we have to just consider my function f x y z equals to 4 by 5, and my function was x plus 2y minus z divided by 2x plus y plus z, and this has to be equal to 4 by 5. So when I solve this, this will be 5x plus 10y minus 5z. This is equal to 8x plus y plus 4z. So taking the coefficients on one side, so I will get 3x minus 6y plus 9z equal to 0, and then this will imply this is just same as x minus 2y plus 3z equal to 0. So this is my corresponding level surface passing to the point given as 1 to 1. So basically to solve the criteria, we just have to do just plug in the point in a function to get the point which I want to calculate the level surface, and then just equate the function with that value which we get after solving the after putting the point, and we get this basically a hyperplane in our in higher dimensions. So that's the corresponding level curve. Is the basically this is the required level surface. Okay, so let's continue. So that's how you calculate the level surface, and it's just not that difficult to calculate. Just you have to plug in the values. So now let us let us consider question number 2. Now we know how to calculate the level surface of a function. Next, we would like to consider basically we would like to calculate the double limits, or basically limits. We need to calculate limits when we have more than one independent variable. So for that, we have one question given as, suppose my function is given as this 2x squared by y whole divided by x square plus y square, and xy being not equal to 0 0, and my function will take value 0 when my point xy is 0 0. Okay, so what we would like to do, we would like to calculate basically the limit as xy tends towards 0 0. So double this particular limit of our function. We would like to see whether this exists. So we'd like to calculate. So first we need to see if it even exists or not. So this is same as calculating the limit of x, y tending to 0 0. And since x, y I'm taking to the limit, so they are not equal to 0 0. So this will be just function at non-zero point, which is 2x square y times y whole divided by x square plus y square. So rule of thumb when you calculate the higher value limits, basically when we calculate the higher value limits, basically higher dimensional limits, so we'll no longer have just a straight line path, we have multiple paths. So if we are approaching any point x naught comma y naught, so like we can approach it through straight lines, we can approach any general curves. So we would like to see many cases whether this limit exists or not. So in theory, you have studied that there is a epsilon delta approach through which one can ensure and guarantees that limit exists. So whenever basically that says whenever our point x naught y naught has basically any point, if I take arbitrary xy, so that it has distance less than delta from our point x naught and y naught, distance being the Euclidean distance I'm taking in R2, then the corresponding our functional value will be nearer to the limit we are in, which we are claiming to be. So it has to be as close as we please. So let's first of all, since x and y tending towards 0, let us compute that how we can calculate this ratio. So one rule of thumb which we can consider in our mind when calculating these type of limits is that we just calculate the degree of numerator and denominator, and if the numerator of the degree is more than the degree of the denominator, so we can ensure that there's a higher chance that the limit will exist. It may not be the case that it always exists, but there's a very high chance that it will exist. So, and whenever this is the case in evaluating the limit at 0 0, the limit will turns out to be 0 0. So let us compute, or let us see how can we bound this function whenever my x and y are small. So what do you mean small? That distance is closer to as close to 0 as we please. So let us consider the function. So it is 2x square y whole divided by x square plus y square. So if I see this, I can write this as twice of mod y times mod of x square whole divided by x square plus y square. Now what can I observe is that x square is always less than equal to x square plus y square for any xy belonging to R2. So I have this thing and this thing is also greater than equal to 0. So I will always have this ratio of x square divided by x square plus y square is always less than equal to 1. So I can take advantage of this fact and I can bound our function or corresponding thing using this. So this is twice of mod y and this is just a less than 1. So this is just 2 times mod of y. So now how we define the distance in Euclidean space or in higher dimensions. So what I would basically like to do to ensure the limit will exist, the formal definition is that we say uh, limit of fxy exists at point x naught comma y naught and say equals L if the formal definition is given as, if I take for any epsilon positive, I'm also assuming the function is also a real valued function. So if I take any epsilon positive, there exists a delta positive such that whenever I'm considering limits, so whenever the distance of x comma y minus x naught and y naught, so the distance from the x naught and y naught is less than delta, will imply the uh, the function value has to be less than that particular L for any epsilon. So this will imply. So what this we mean by that, whenever my points are basically in a neighborhood of x naught and y naught. So if this is my circle of radius delta, so whenever my points are in this radius or in this center, in this disk centering at x naught y naught and having radius delta, this will imply that my function value has to be very close to L, as close as we please. So so this is our required definition. And what do we mean by this thing? This thing is basically saying either under root of x minus x naught square and y minus y naught square. So this mod means this particular Euclidean distance in R2. And similarly, we can generalize for the Rn thing. So if we have x naught, y naught, z naught, or up to some x1, y1, x1, x2 up to xn, so then this is us, you take the square root of the x1, x minus x1, uh, y minus x2, and so on and so forth. So that's the Euclidean distance you are considering. So now we can see that. But we can see that we have shown that our function is bounded by twice of mod y, right? So we have fxy bounded by twice of mod y, and we can observe that we can write this as mod y as square root of y square, and this is less than twice of x square plus y square, and so this is less than delta. So my function value is less than delta and I want it to be less than epsilon. So I want this thing to be less than epsilon, and this can only happen if I take delta to be epsilon by 2. Then what will we have? That the mod of fxy that will be less than twice of delta, and this is just basically this is equal to twice of epsilon by 2, and this is just epsilon. So this proves that basically my function mod is going toward 0. So this basically saying, this basically proves that the function, this thing is same as saying fx y minus 0. This thing is less than epsilon whenever modulus of x comma y basically minus 0 0, and let me write this, x comma y minus 0 0 less than delta, and where I'm taking delta to be epsilon by 2. So this will imply that this the limit of x y tending towards 0 0 fxy is nothing but equal to 0. So it is one of the ways to prove the limit will exist. So one thing which we can see, this is bit like it's easier in some cases, but it's not that easy in general when you're proving that the limit will exist. So I will show you one more method to solve this question, to find and evaluate the limit of this function at 0 0. So that method is more easier and more handy and easy to compute. So that method is using the polar coordinates. Okay, so we will use the polar coordinates to compute the limit. Okay, so let's start. So we would like to consider this limit x y tending towards 0 0 of 2x square y whole divided by x square plus y square, and so this will be I can transform into polar form. So I will take x equal to r cos theta and y equal to r sine theta. So then this limit will be equivalent to limit of r tending towards 0 to r square cos square theta, and this will be r sine theta. This whole divided by r square only. So this is equal to limit r tending towards 0. So this will be just twice of r cos square theta and sine theta. So now note that one thing, that these thing cos square theta and sine theta, this thing is bounded. So this whole thing twice of r cos square theta sine theta is bounded above by 2 twice of r times 1, because cos square theta is again bounded by 1 and sine theta is again bounded by 1. So this will be just 2r. So as limit r tending towards 0, so I can use the squeeze crack theorem, or basically the comparison principle, to conclude that this limit r tending towards 0 to r cos square theta sine theta is 0 as 2r tends to 0 as r tending towards 0. And we can see we can easily compute the limit with just putting the just substituting the polar coordinates and just directly evaluating the limit. So this is much easier method in most of the cases. So you one rule of thumb is, just whenever you see just these x square plus y square sort of terms and these type of things, or when there's a high degree in the numerator, so try to approach through a polar coordinates. There's a very high chance that you can directly compute this limit with just using the polar coordinates. So with this we can complete this. We have completed this question, and I've told you two methods to solve this question. So in this question, so finally we can say that limit at 0 0 exists, and we have shown it with two methods. Okay, so next another type of question which I'd like to tell you, so that you can easily able to solve the assignments given in the on the website. So let's start with another question. So my next question is let's say I'm defining a two variable function as fxy is equal to sine of xy. So this sine xy, so and my this function is from R2 to R. So I would like what I would like to do. I want to like to do find the range of this function. So how to proceed this? So we would like to find the range of this function. So we would like to consider all the possibilities of my points x and y in R2, and we would like to see what are the possible values turns out to be. So what you guys can see, I know that this is a sine function, and sine function takes values between -1 to n1. So one thing is for sure that the whatever the range of function has to be contained in the range of uh, it has to be contained in the range of sine function, right? Sine of, let's say, some z, and this is just nothing but -1 to 1. So whatever range of this function that will has to contain in this interval -1 to 1. So what our claim would be, the range of this function is actually turns out to be the whole -1 to 1. And how can we show this? So what we can do here, our x and y are could be any real number. So let me take y to be equal to 1, and we would like to see what happens when we vary x over the whole real line. So then this will imply my function fx1 would be just sine of x only, and my x can vary on the real line. So this fx1 will take any value between -1 to 1, because my then this will imply that fx can take any value between -1 and 1 as x belongs to R. So this will imply these all of these values -1 to 1 are achievable. So and this will imply that this -1 to 1 is actually contained in range. But as we have shown, that range has to be in this interval only. So this will actually imply that range of my function f is -1 to 1 only. Okay, so that's how you basically calculate the range of my function. So instead, if you have sine xy, we could have x plus y or something like that. Try one more question. So let's say if you would like to range of fxy as x plus y. So again, we can my x and y where my function is from, again R2 to R. So again, what we can see that if I fix my y, let's say let y to be 0, then fx 0 is just x, and I know that for any x, my function will take value x, and that implies f will assume any real number. So this will imply that actually the range of this function f will be equal to R in this case. So that's how you basically can check. You can take particular cases of one variable, fix one variable, and then vary the other variable to get the idea of the range. And after some calculation, you are able to reduce what the range of my function f is. I hope that's clear. So let's proceed, and we would like to see we know the function is continuous. So we basically would like to see how these epsilon delta values can be numerically, like one example where I take some particular value of epsilon and we would like to see what particular value delta I get. So to get basically to make things more clear. So let's start with another question so that we can have a more clearer picture of how this epsilon delta works in the higher dimension. So let me consider another question. So I'm considering my function, another two variable function, which is given as x cube plus 3y cube whole divided by x square plus y square. and where this is when my denominator is non-zero, and that happens whenever my denominator is whenever my x y are not equal to 0 0, and I'm taking value equal to 0 whenever my x and y are equal to 0 0. So what I would like to do, what is the condition on delta for which what I have fxy minus f00 is less than 0.1. So in this case, what I'm taking my value of epsilon equal to 0.1. So I'm taking a particular choice of epsilon. So I would like to see what are the values of my delta so that this thing basically holds. So let us try this question. So like as we did in earlier questions, so we would like to see that how we can estimate this particular ratio, and we would like to see how we can bound with respect to the distance of our function x and y from 0 0. So let us consider this ratio. We would like to see what kind of bounds we can have on this ratio. So let us consider this thing. So this is x cube plus 3y cube whole divided by x square plus y square. So we would like to bound this ratio. Okay, so with respect to distance. So this can be written as x times, if you observe, x times x square plus y square and plus thrice times. So we are using the triangle inequality here. So I can write this as less than equal to thrice times mod y square x square plus y square. Okay, and as this is coming from the triangle inequality. So what we can do now, let us bound this. So I know this ratio, this particular ratios are less than equal to 1, as you've seen in the question number first. So again, I can bound this by mod x times 1 plus 3 times modulus of y, and again this can be bounded by 1. And again, what we can do, this mod x can be written as under root of x square and 3 under root of y square, right? And this is less than equal to x square plus y square, and this is thrice times x square plus y square. This is 4 times under root of x square plus y square. Now, but I want this thing is less than 4 times delta, because I know the delta is chosen such that my point being 0 0. So this will imply this x minus 0 square plus y minus 0 square, this under root of x square plus y square. This thing is less than delta, so then that's why I'm taking here this to be less than delta. And what I want this whole thing to be less than 0.1. So that's what we started with earlier. So I want this condition of this thing. I want that my function value with the 0 0 has to be less than 0.1. So that's what I want. So to have this, what like to have is delta. If 4 delta is less than 1, then our condition is satisfied. So this is hold only if and only if my delta is less than 0.1 by 4, and that is nothing but 0.025. Okay, So this will imply if I take my delta to any number delta which is less than 0.025, this will imply that my function fxy, the modulus of that has to be less than 0.1. So we get a numerical estimate on a delta given a particular value of epsilon. So that's how you can basically calculate the values of delta. So I hope that makes this calculation of epsilon delta more clearer with how things work. So let's now proceed, and what I would like to now next tell you guys that whenever we consider this before going to the question number 5, so one thing which we have seen is that this limit. So let's start the question number 1 first, and let's have some theory. So my function is fxy is given as x cos 1 by y, where my y is non-zero, and I'm taking it to be 0 and my y is 0. So what I have to do, evaluate three things. Limit x comma y tending toward 0 0, fxy, first thing. Second thing which I would like to evaluate the iterated limits. So let me write that first. I would like to evaluate the iterated limits. So iterated limits. Okay. So iterated limits. So limit as x tend to 0, and then limit y tending to 0 of fxy. And what else I would like to evaluate is the limit, the other iterated limit. Okay, so one thing which we have seen in our the multivariate calculus course is that whenever we have a double limit exists, this will imply the iterated limit exists and they are equal. But there is one more condition which we have considered, that we also assume that this iterated limit has to exist beforehand. Otherwise, we cannot say that limited iterated limit exists. So this is one of the examples which basically explores this idea, which says that if I consider basically what we will see in this case, we have a existence of a double limit, but still one of the iterated limit does not exist. So the theorem which we have studied in our course uh, shows the importance of the existence of these iterated limits. So that's one of the things, important things which you have to keep in mind, that to ensure that whenever my double limit exists, the iterated limit exists. If and only if well, basically we have to assume that iterated limit has to exist. So let us evaluate the limits. So let's start. So now what our function was given as fxy equal to x cos 1 by y, where my y is non-zero, and we have a 0 whenever my function y is 0. Okay, so let us start with this question. So I would like to evaluate the double limit first. So what I will do, I will just again consider the modulus of our function, so x cos 1 by y. So I know one thing, that my cos function is bounded above by 1. So this whole thing, whenever my y is non-zero, this can be bounded above by mod x. times 1, which is just nothing but mod x. Okay, so I know again this mod x is less than the same technique which I've used earlier. So this is just under root of x square plus y square, and this is nothing but this is less than delta. So I would like to have this thing to be less than epsilon. So I just take delta to be epsilon. So this will imply x cos 1 by y less than epsilon whenever under root of x square plus y square is less than delta, which where my delta is given as epsilon. So this will, with the epsilon delta definition, what we have here, we have basically the limit of this double limit basically exists, and this exists and is equal to 0. So we have basically limit x y tending towards 0 0 x cos 1 by y. This exists and this will be equal to 0. So next we will see iterated limits. What happened to the iterated limits? So time for iterated limits. Okay, so let's start with iterated limit. So let's just consider the first iterated limit, limit y tending towards 0, limit x tending towards 0 of x cos 1 by y. So I know that this cos 1 by y is a constant here whenever my y is non-zero, and I'm taking x to tending towards 0. So this thing will be just a bounded constant and another variable which is tending towards 0. So this will be just nothing but the limit turns out to be 0. The first limit when we take x tending towards 0, so this will be just 0. So the limit of 0 sequence is 0, or so this will be a 0 function 0, so this will be just 0 itself. So in this case, this particular iterated limit exists, and it has to be equal to 0, value 0, which is the value of our double limit, right? So next we have another side iterated limit. So this will limit x tending towards 0, limit y tending towards 0 of x cos 1 by y. But we can see in this case as limit y tending towards 0, cos 1 by y does not exist. So basically limit as I tending to 0, but this thing the inner limit does not make any sense. So at the end we cannot take any limit, then this ultimately this will imply this whole thing does not exist. And why this happens? Because I know that limit y tending to 0 cos 1 by y does not make any sense. It will oscillate between -1 and 1, so it will not converge to any particular number. So this actual limit does not exist, and this will create issues. And we actually have iterated limit also does not exist in this case. So this actually shows the importance that to claim that the iterated limit will have the value equal to the double limit, we have to ensure that the iterated limits has to exist. So this question basically tells the importance of the existence of our iterated limits. So I hope that clears the idea behind the iterated limits and their existence. Okay, so now we have seen some ways to evaluate the iterated limits, and then we have also seen some basic how to calculate the level surfaces and other things and all. So moving on, next you guys have studied the partial derivatives. So we would like to generalize the idea, basically generalize the basically the derivative in variable to higher dimensions. So the first thing which will encounter the derivative is the partial derivatives. Those basically taking the derivative in particular directions, or in particular, I'm taking the x direction and the y direction. With respect to the x direction, what I'm getting the partial derivative with respect to x. And in that y direction, I'm getting a partial derivative with respect to y. Okay, so we'd like to see one question on based on the partial derivative. So let us start. Okay, so let's start with the question number 5. Question number 6. So I will consider one function. So my function is another two variable function. Which is basically given as y times x square minus y square whole divided by x square y square, and then we have a 0. So this is whenever my x y are not equal to 0 0, and this is whenever my x y has to be equal to 0 0. Okay. So what I would like to see, I have like to evaluate partial derivatives, and in particular I would like to evaluate the partial derivative with respect to the y variable. So I would like to see what is my partial derivative with respect to y variable at point x comma 0, or I can denote it as del f by del y at point x comma 0 0. Okay, so how to proceed this? To proceed this, what we basically do, we would like to just apply the definition of our partial derivatives, and let's see what our limit is actually turns out to be. So let us start. So my function is this. So how do we calculate the partial derivative with respect to y? So let me write the definition first. So I would like to see the fy at x comma 0. So this is limit k tending towards 0. So what I will do, I have to just change the variable in the second variable only where my y coordinate is. So what I will do, I will consider x comma k minus x. I will keep the other things constant and just have to change the variable in this, change the second variable where my y is there. So it is fx comma k minus fx comma 0 whole divided by k, and I have to tend k towards 0. Okay, so let us see what are my values of my function. So limit k tending toward 0, I have to see what is fxk, and that is, if you see, this will be k x square minus k square whole divided by x square plus k square. And if we have to see what is my fx0, right? So let us go back to here. So if you see my y fx0, so whenever my when my x is 0, though then f00 is 0. When my x is non-zero, so I have to see what my fx0 is. So fx0 when my x is non-zero, so it is 0 times x square minus 0 whole divided by x square plus 0. So denominator is non-zero, so this will be just 0 thing. So in any case, I'm getting my fx0 to be 0 itself, so this will be minus 0 and whole divided by k. Okay, so if I simplify this equation, so what I will get, limit k tending towards 0 x square minus k square whole divided by x square plus k square. So if I tend k towards 0, so I can see that this limit will tend towards where x square divided by x square. So this will be just x square minus 0 whole divided by x square plus 0. And this is what? This is just nothing but x square divided by x square, which is equal to 1. So this will, but this will not, therefore what we have, fy at x comma 0 turns out to be 1. Okay, so I think that makes that clears the how to calculate the partial derivative with respect to y variable. We just have to just put the definition and just evaluate the limit. That's all we have to do here. All right, so if you know, let's calculate the partial derivatives of one more function. So let us consider another function. So another question. I consider the function to be x square y plus 5x y square 2x plus y square. So this is my again a two variable function which we have here, and that two variable function, what we would like to see, we would like to calculate the let us calculate the partial derivative first, and so calculate fx. Let's say that I will this time will take the point to be 1 comma 0, and let us again calculate the partial derivative with respect to y at again 1 comma 0. Okay, so again since this is a function, is a polynomial in x and y, so these functions are very nice functions and they are differentiable. They are very easily differentiable, and so we can directly apply the derivatives which we used to do in one dimension. So we can directly calculate. So the partial derivative with respect to x, I just have to differentiate this function with respect to x and keeping the variable y as a constant. So this will be 2x by 5y square plus 2, and this will be just a constant. So this y square will turns out to be 0 when I differentiate with this partially differentiate with respect to variable x. Okay, and similarly I can consider my partial derivative with respect to y. This will be just x square 10x y. 2x will be 0 again. This is a constant when I partially differentiate with respect to y only, and value of 2y. Okay, so next I just have to calculate my value at 1 comma 0. Okay, so del f by del x 1 comma 0 will be, so first term will be 0, second term will also be 0, and this will be just left with 2 value. So this is my 2, and if I consider the partial derivative with respect to y at 1 comma 0, so this will be what this will be, this will be 1, again 0, and another 0. This will be value just equal to 1. So that's how you can calculate the partial derivatives. Like if you already know the function is differentiable, you can just directly differentiate and like differentiate with the variable which you are considering, and treat the other variables as constant, and you can just calculate the partial derivatives. Okay, so one more thing which I like to point. So someone can ask question like this. So let me write. So find the slope of the given function in the x direction at point 1 comma 0 is, basically we would like to find the direction. So so this is nothing but saying that we would like to find the partial derivative of my function with respect to x, because this is the basic the what partial derivatives mean. So this is basically the slope of my given function in x direction. So this is just same as evaluating the del f by del x at the point 1 comma 0, and which we have basically evaluated earlier, and this turns out to be equal to 2 only. So this will be just 2 equals to 2. So the idea is simple. So one can one can ask questions in a more different way, but if you know what they are asking, it's very easy to calculate the partial derivative. So that's what I'd like to add to this question. So next, so now, like, I think we are good at calculating the partial derivatives. So let us consider another question. which is more like based on the continuity. So again, let's get back to continuity one more time. So let's consider another fun question number 8. So again, I'm considering if my function is given as x power 4, y power 4, whole divided by x square plus y square. Then we have k, and then xy has to be not equal to 0, 0. And it takes the value k when my xy are equal to 0, 0. So what I would like to do, find the value of k for which f is turns out to be basically continuous at point 0, 0. Okay, so we'd like to find the values of k for which basically this function it turns out to be continuous. To how to see a function to be continuous, let us recall the definition. So it says that first thing, so f is continuous, let's say at x naught y naught. So for that, what is the criteria? Basically, the first thing has to be the double limit should exist. X and y, I'm tending towards x naught, y naught, fxy. This has to exist. Second thing, which I would like to have is that this limit thing exists, and this has to, let's say, exist, and let's say, and it has to exist, and one more thing which you like to have, this whenever this exists, this has to be equal to at the point x naught y naught. So this thing has to be equal to, so since this exists, I can consider this value and try to see if this value turns out to be equal to the point at which I'm taking the continuity. So the second condition which I should ensure has to be the function has the value of the function at that point x naught has to be equal to the limit, the double limit which I have calculated, and turns out to be, if these things are equal, we say my function is continuous at point x naught comma y naught. So to find the value of k, first we have to calculate the double limit x comma y tending towards 0, 0 of our function fxy. So this is limit x comma y tending towards 0, 0 of x raised to power 4 y raised to power 4 whole divided by x square plus y square. Okay, so again this is in the same situation, so I have to evaluate this limit, right? So to evaluate this limit, I have again lots of ways to calculate this limit. The methods like which we have discussed earlier, so we can again start with the epsilon delta definition to calculate this limit. Well, one can also use the polar coordinates to evaluate this limit, but it depends on person to person how you would like to evaluate the limit. So let us try with the usual epsilon delta definition, and let us start with that by bounding the function which we have. So I will have to consider the absolute value of x raised to power 4 y raised to power 4 whole divided by x square plus y square modulus. Okay. So what I will do, I can see that this thing can be, a triangle inequality can be bounded by x square plus x square plus y square plus y square x square whole divided by x square plus y square. So what I would like to do, now we use the same thing which we have used so many times now, that this whole modulus is again bounded above by 1, so I can bound this thing by 1. So we have done this thing multiple times. The whole thing is bounded by x square plus y square. Okay, so now I know this thing is less than what? This thing is less than what? This thing is less than delta square. And how are we getting this? We know that square root of x square plus y square is less than delta. So we have this thing is less than delta square. Basically, we have squared on the both of the sides. And I want this thing to be less than epsilon. To have this, basically what we can choose delta to be square root of epsilon. And again, this is a positive quantity because epsilon is positive. So I can take the positive square root, and this thing is again turns out to be positive. And what this will imply? This will imply that mod of fxy is less than delta square. But again, this is just root of epsilon. So this turns out to be equal to epsilon whenever square root of x square plus y square, like we have to take at the point 0, this is less than delta. Okay, so that's basically tells that the double limit exists and equals to 0. So I have limit x comma y tending toward 0 0 fxy. This is equal to what? This is equal to 0. But I know that it had for continuity. So let me write on the next line. For continuity, we need k to be equal to 0. So this actually implies k has to be equal to 0 to ensure that function is continuous at point 0 0. So the value of k which we have to take is k equal to 0, and this will ensure that the function is continuous at the point 0 0. So I hope that clears this part. Okay. Okay. So now moving forward, we have seen a lot of examples in which we have seen that the limit will exist, but let us see and let us one example where we can see that our limit will turns out to be doesn't exist, and how to basically show that limit doesn't exist. So let us start with one example. So one more question. So my function, let us take my function to be equal to x plus y whole divided by x minus y whenever x is not equal to y, and otherwise I'm taking the value equal to 0 whenever otherwise basically whenever x is equal to y, I'm taking my function to be equal to 0. So um, so let us check whether limit x y tending towards 0 0 of fxy exists or not. Okay, so let us consider. So this time the rule of thumb which I have stated back in earlier of this tutorial session, that I have told you guys that this rule of thumb that if the numerator degree is more than, then we can ensure that the limit will exist. But as soon as the degree of the numerator turns out to be less than equal to the degree of the denominator, we can there's a huge possibility, there's a very high chance that the limit is not existing at some point. Generally the point is generally the point where where the limit will not exist is the point where the denominator turns out to be have singular points. So what do I mean by singular points? They have basically vanishing at those particular point. So so in this case, our rule of thumb actually works, and we can actually we will see that this actually double limit will not exist in this case. And to formally prove this, what we can do, we can take paths. Basically, to approach 0, 0, we can take many paths. So one of the paths, the standard path which we take is the straight lines with different slopes. So I take y equal to mx. So this is a path which passes through 0, 0. So I have to also ensure the path which I'm taking has to pass the point where I'm actually evaluating the limit. So if let's say if I'm evaluating the equation at 1, 0, so I have to consider the path something like y equal to m x minus 1. So basically we have 1, 0 has to be lie on the path which I'm considering. So that's the main point. So that thing you have to keep in mind. Okay, so that's one thing which I have to mention. So let us get back to our question. So I have to consider limit x comma y tending toward 0, 0 fxy, limit x y tending toward 0, 0 of x plus y x minus y, because otherwise it will be 0 only. So I'm considering that other parts, and this will be just same as saying the limit x tending towards 0. If I consider this particular path, I just have to substitute y with mx. So this will be x plus mx whole divided by x minus mx. And if I take x to be non-zero, this turns out to be value. What is this? This is just 1 plus m whole divided by 1 minus m. And if you see, this is not independent of m. So if I take m to be half, or let's say 1 or 2, the limit will turns out to be different. But we know one thing, that limit, if it exists, it has to be unique. And that's not happening here. And this basically will imply that the limit does not exist in this case. So since we have dependence on m, the limit doesn't exist. Okay, so that thing that clears, since limit has to be unique, but we're getting different values of limit if we take different paths. So in this case, we don't have a limit to exist. Okay. Okay, so let's move forward, and let's have some more questions. So let's solve another question. Suppose we have a function ex plus y square. So what I would like to do is to let's have some calculations, and just to have basically more handy on these calculations, and to get these calculations more have to easily calculate things. So let's have this question, and we will basically what we would like to have. We would like to have like then find beta such that fx at 1, 1 partial derivative with respect to x plus beta times fy at 1, 1. This has to be equal to the value at 1, 1. So we'd like to see what value of beta will give this equality, or whether any beta even works or not. So let us start. So for this, we have to calculate the partial derivatives with respect to x and y. So again, we have this polynomial function in y and this exponential function in x. These are very well behaved functions and are differentiable. So we just directly calculate the partial derivatives. So let us compute the partial derivative. So the partial derivative with respect to x, when I calculate on ex, this will be ex only, and when I take y squared, it will be just 0. So this will be e raised to the power of x. And if I calculate the value of y, so since ex contains no terms of y, this will be treated as a constant. So this will be 0 plus twice y. So this is just the derivative by 2y. And but I need to calculate the partial derivative with respect to x at the point 1, 1. So this will be e raised to the power of 1, which is just e. And if I would like to consider the partial derivative with respect to y at the point 1, 1, this will be just 2 only. And finally, the value f11, this will be e plus what? E plus 1 square. This is e plus 1 only. So, but do we have it? We have fx 1, 1 plus beta times fy 1, 1. This has to be equal to f what 1, 1. And this will imply this has to be equal to e plus beta times 2 plus e plus 1. So this will imply e is cancelled out. So we have beta equal to half when we solve this equation. So we get beta equal to value equal to half. So basically you can calculate values and equate things and just put things in the equation, and just this is computation. So I think that's all. Yeah. Okay, so now we have seen some questions. So let us move forward and let us try some more questions on the double limits to have a better understanding of the double limit. So let us proceed. So the next question which I would like to consider is question number 11th. So examine if the limit is x comma y tending towards 0, 0 exists. Okay, and what is our limit? We would like to see the limit is x comma y tending towards 0, 0 sine xy whole divided by x square plus y square. Okay. So how to evaluate this limit? Basically, let us see that if we just have a rule of thumb to just have a guess what would be the limit of this function. So the first guess which we have to consider to like the candidate for the limit, we just evaluate the iterated limits. So candidate for the limit. So I have to evaluate the iterated limits. Okay. So limit as y tending towards 0, limit as x tending towards 0 of sine xy whole divided by x square plus y square. Okay. So this will be limit y tending towards 0. So I know for any value of non-zero value of y, the denominator is non-zero, even if my x tending towards 0. So, but the numerator also tend towards 0. So this will be 0 divided by some non-zero number. So this limit will turns out to be 0. And this is 0. So the candidate for the limit, if it exists, it has to be 0 only. Okay. So if it exists, we have to see it has to be 0 only. So one more thing which we have to check first, we will take the paths one more time, y equal to mx paths. And we will see, let's see if we can have something dependence or not. If no dependence is there, so we try to prove the limit is 0. The candidate which we have found earlier through the by evaluating the iterated limits. Okay. So let us start. So let us take the different paths and let us plug in our limit. So this will be limit x comma y tending toward 0 0 sine of xy whole divided by x square plus y square. This will be just limit of x tending towards 0 sine mx square, and this will be x square plus m square x square. Okay, so like what we can see, this can be seen as limit x tending towards 0 sine of mx square whole divided by x square and times 1 upon 1 plus m square. Now we remember one more standard limit which we have calculated in our one variable calculus is limit as x tending towards 0 sine x by x is equals to 1. So we can see the same thing is sort of is there. So instead of x we have m times x square. So I have to multiply by m here and multiply by m here to nullify the effect. And now we can see that this thing is m times 1 plus m square, and this limit will turns out to be equal to 1 from our one variable calculus course. We know that this is equal to 1. So this will be m upon 1 plus m square. So this turns out that for taking different paths, we are getting different limits. And again, if the limit exists, this will not be the case. So this will imply that limit actually will not exist at 0 0. So which basically depends on m. Thus, limit doesn't exist. Okay, so limit is not existing in this case. So let us consider more examples. Let us evaluate one more question. So if we have a question, like to see the limit as x comma y tending toward 0 0 x y cube x square plus y to the power 6. So check whether the limit exists or not, whether the limit exists or not. Okay, so let us start. So again, we evaluate the iterated limits to have a idea that what could be the candidate of the limit. So limit x tending towards 0, limit y tending towards 0, x y cube x square plus y to the power 6. So this will be whenever my x is non-zero, the denominator is non-zero. When even my when tending towards 0, so this will denominator is non-zero, but the numerator is 0. So this will be just the limit turns out to be 0. So this is limit x tending to 0, and this limit is 0 for any non-zero x. And when I'm extending towards 0, this will be 0. So this will be my candidate of my limit. So now let us see what can we do. So if I take the normal paths, y equal to mx, limit x y tending toward 0 0 of x y cube x square plus y raised to power of 6. So this will be limit x tending toward 0 x times m cube x cube. So x raised to power 4 is there, and then we have x square plus m raised to power of 6 x raised to power 6. So this will be just limit x tending towards 0 m cube, and I can take the x square out, so this will cancel out. So m 1 upon m raised to power of 6 of x raised to power of 4. Okay, and then we can see then this turns out to be equal to 0 for any m. So on the straight lines, we don't have any issue. So this seems to be like the case that limit is existing in this case. But these are not on all the paths which are basically approaching towards 0 0. So there could be any other paths. One thing which we can observe here is that there's a homogeneity. If you see, if I take y equal, if I take equal to, if I take let's say x equal to something like y cube, in the numerator we have balancing out factors there. So we have the degree matching things are happening. So if I take x equal to y cube, then the ratio which we have here x y cube whole divided by x square plus y raised to power of 6. This can be written as y raised to power of 6 whole divided by 1 plus, so this will be, sorry, 1 y raised to power of 6 plus y raised to power of 6. This will be just half. So we have, and so if you evaluate the limit x y tending towards 0 0 of x y cube whole divided by x square plus y raised to power 6 on this path, so this will be limit y tending towards 0. So now we have x in y of terms, then this will be y raised to power 6, y raised to power 6 plus y raised to power 6, and this will be just half only, and this is not equal to 0, which we were getting earlier. So this will imply again the limit is coming out to be different, but the limit exists, it has to be equal on all the paths which we have considered. So we got one path where we're getting different limit, and this will, what will this will get, this will give us, we are getting different limits, and the limit doesn't exist because we are getting different limits. So as we are getting different limits along different paths, this implies the double limit doesn't exist. Double limit doesn't exist. Okay, so I hope that's clear. So let us proceed. So what we all can discuss now, we can have another. Let's have some different type of function. So let's start. So we have here another different type of function. Let me see how much questions we've covered till now. We have till the 12. So the next question is, so for the 13th question, so let's consider one more function. So we would like to see the continuity of the following function. So examine the continuity of the following function. Okay, so the function given is fxy sine square x minus y whole divided by mod x plus mod y whenever my xy, and this is 0 whenever otherwise, or I would say whenever my xy equal to 0, 0. So we like to see the continuity of the function. So as mentioned earlier, to check the continuity of the function, we have to just evaluate the double limit. It has to exist, and when it exists, it has to equal the value at the point of my function. Okay, so let's see. Let us see first. To check that, we consider what we consider. We consider the iterated limits to get an idea that what could be the possible candidate of our limit. So I've considered limit x tending towards 0, limit y tending towards 0 of sine square x minus y whole divided by mod x plus mod y. Okay, and so when I take y tending towards 0, so this will be limit x tending towards 0 sine square x whole divided by mod x. So this is non-zero, so I can evaluate limit in this fashion. And as x tend towards 0, so again I use the result that this can be written as limit x tending towards 0 sine square x square times x. This can be written in this fashion also. And again, I know that sine x by x as limit x tend towards 0 is 1. So this will be just, this thing is actually turns out to be bounded thing. So this will be bounded above by 1. So, and this thing tend towards 0 as x tend towards 0. So a bounded times a limit which tend towards 0 can be shown that has to be equal to 0. So this will be 0 equal to 0. So we got one candidate for the limit. So what we can now see, let's try to bound this function basically whenever my x y tend towards 0. So let us consider sine square x minus y whole divided by x plus mod y. Okay, so I have to subtract it from 0, but that's the same thing. So we are just skipping that part. So this is we are using one more inequality, that this thing has sine. Basically we have here mod of x minus y square whole divided by mod x plus mod y. And what we are using here, the mod of sin x has always less than mod of x. So this is, we are basically using here to get this inequality here. And finally, what we would like to do, we would like to see that that this mod of x minus y, and this can be written as mod of x minus y, and we have to divide by mod x plus mod y. And again I can use the triangle inequality. So this will be mod x plus mod y whole divided by mod x plus mod y. And when I see, this will be just mod of x minus y times 1. So this is just mod of x minus y. And now this again can be bounded by mod x plus mod y. And this is just under root of x square plus y square plus y square plus x square. And this is less than twice of delta. So I can use the same arguments to consider that if I take delta to be epsilon by 2, then my fx by their modulus is less than epsilon whenever x square plus y square, the square root of this thing, is less than delta. Okay, so whenever this is less than delta, we are getting, and where I'm taking delta to be epsilon by 2. Okay, that's basically proves the limit exists and it has to be equal to 0. And since my functional value at 0, 0 is also 0, so this will imply the function is continuous. Okay, so as limit x comma y tending towards 0, 0 fx y, it is 0, and this is equal to functional value at 0, 0. This implies f is continuous at x y equal to 0, 0. Okay, I hope that clears this particular question. So let us, you guys can just see, you have to just first calculate the iterated limits to have an idea that what could be the limit, and then try to bound the function, and you will see eventually that whether you can bound or not. If you can able to bound the function, you will get the continuity, and if not, then you try different paths, and with different paths eventually you will get that with some different paths you are able to get different limits, and this will actually imply that the actual limit will not exist, and the function is not continuous. Okay, so I hope that's clear. Let's move forward and let's try to solve some more questions. So we can have some more questions. So okay, so let's start with one more question. So that was question number 13. So okay, question number 14th. Okay, so what we would like to do, I have to examine if the limit as x comma y tending towards 0, 0 exists or not. Okay, so it has the function which I'm taking is fxy is xy x square minus y square whole divided by x square plus y square whenever my xy is not equal to 0, 0, and 0 whenever my xy is equal to 0, 0. Okay, so let us try to evaluate if the limit, if this particular limit exists or not. So we will start with the same standard approach. Okay. So first let us evaluate the iterated limit to see what could be the value of our limit, if it even exists or not. Limit x tending towards 0, limit y tending towards 0, x y x square minus y square whole divided by x square plus y square. And if we see this is y tending towards 0, the numerator is non-zero. So this will be just it will tend towards 1 only, and x is constant. But as y tending towards 0, y will tend towards 0. So this whole limit will tend towards 0. So this will be equal to limit as x tending towards 0 of 0, and this is just 0. So if the limit will exist, it has to be equal to 0 only. So now let us bound our function, which we have done so many times. So let us do one more time. X square minus y square whole divided by x square plus y square. Okay, so let us consider. So now what we can do, we can have bound this by mod x mod y, and then we have x square minus y square whole divided by x square plus y square. Okay, and then again this can be bounded by mod x mod y, and this is mod x square plus mod y square, again by triangle inequality, by triangle inequality. So this is just mod of x plus mod of x times mod of y, and that is less than equal to square root of x square plus y square, and again this is less than equal to x square plus y square, so this is less than delta square, and so I want this to be less than epsilon. So what I will do, I will take delta to be epsilon root. So this basically will imply that mod of fxy is less than epsilon whenever mod of x square plus y square, mod square root of x square plus y square, mod of xy is less than delta, and where I'm taking my delta to be square root of epsilon, which is positive. Okay, so this implies that limit x comma y tending toward 0 0 fxy will exist, and this is equal to 0. Okay, this will be equals to 0. Okay, so I hope that that's clear. Next, one more thing which I like to now mention is the one of the things which basically we saw in lectures, that if my partial derivatives, like we have seen that if partial derivative exists in higher dimension, like in the one dimensional case, we have seen that function is differentiable, that will imply continuity. But in higher dimensions, we have seen in the lectures, if the partial derivatives exist, this will not imply the function is continuous. And also if the function is continuous, that will also again not imply that either of the partial derivative will exist. But there was one theorem which was mentioned in the end, that if what we have here, if we have basically partial derivative exist and are continuous in a neighborhood, then that will imply the function is continuous. So let us try to prove that thing. Okay, so let me write on the statement. So the statement is, let f be a two variable function such that the partial derivatives exists at x naught comma y naught, and not only that, we have also and are continuous in a so let us consider the last question of the last question. So till now, but we have seen that if I consider a continuous function, it may not imply that partial derivative will exist, and also if the partial derivative exists, this will also again not imply that the function is continuous. So this is a very different thing which we see in multi-dimensional case, because in the one-dimensional case we saw that if the function is differentiable, this will imply continuity. So that sort of thing is not happening here, and this will gives one of the this will give that the function, if turns out to be if to be differentiable, partial differentiable, this will not give continuity. This will give that partial derivatives are not a good thing to be considered as a considered to be as a function to be differentiable, to be called as differentiable, because if the function differentiable, it has to at least guarantee continuity, and which we are not getting with help of only the partial derivatives. So they are not good, very good as be considered to be function to be differentiable. But one thing which you like to see in this last question, that if the function has partial derivatives exist in the neighborhood, and not only that we have the continuity of the partial derivatives, then we can ensure that the function is continuous at that particular point. So that's basically that question is, if we also assumes that the partial derivatives are continuous in the neighborhood, we will get the continuity of our function at that particular point. So we like to prove this. So how we are going to prove this? We are going to prove this just considering the definition. So I just consider the function fx5, and I consider it's the difference with the point fx naught y naught. So I would like to use the partial derivatives. So one of the main theorems which connect the function and its partial derivatives is the mean value theorem, which we have studied in one-dimensional case. So we would like to employ the mean value theorem, so of the one-dimensional case. So to employ that, because that's one of the things which connect the function and derivatives. So what we have to do, we have to just this difference have two variations, both in the x direction as well as in the y direction. So we would like to separate these variations. So how we would like to deal with that? We just consider the difference of, we just added and subtracted fx naught comma y, so that we can separately consider the x direction difference and the y direction difference. Okay, so I've just added and subtracted fx naught comma y, and then with the help of the triangle inequality, I can bound this thing by fxy comma fx naught y and fx naught y comma minus fx naught comma y naught. Okay, so in the first thing we have a change in the x direction only, and in the another difference we have the change in the y direction only. So we have basically successfully separated the differences. Now we can apply the mean value theorem of one-dimensional case to basically write the first difference as, since the variation is coming in the x direction only, I can write this as thing with the help of mean value theorem, del f by del x at some point zy, which is lying between x and x naught comma y times x minus x naught. Similarly, I can write that this difference fx naught y minus fx naught comma y naught to be the partial derivative with respect to y at point x naught comma w, where w is again another point lying between y and y naught, and this is multiplied by y minus y naught. Okay, so now this thing we have here is, so now but we can use this, the assumptions we have taken, that the partial derivatives are continuous in a neighborhood. So if they are continuous in a neighborhood, so I can choose one neighborhood where these partial derivatives are bounded. That's the main crux. I can use the assumption to get these partial derivatives are continuous in a neighborhood. This will imply this, I will have some delta naught, so that in that particular neighborhood we can choose that neighborhood such that these partial derivatives are bounded. So they are bounded, and let's say they are bounded by some number m, some positive number m. Okay, so but basically we have here, so that difference will be again bounded up by m times mod of x minus x naught plus m times mod of y minus y naught, provided we are in that particular neighborhood. Okay, and finally this x minus x naught is less than delta, and y minus y naught is less than delta, as seen so many times earlier. So finally this difference will be bounded up by twice of m times delta. So I need these things to be less than epsilon. To have this thing less than epsilon, I want my delta to be also less than epsilon by 2m. And to have this bound, I also want my delta to be less than delta naught. So if I take delta to be minimum of this epsilon by 2m and delta naught, I have this whole difference to be less than epsilon. So basically this is the definition of my continuity. So if I choose my delta, I found one delta, so that whenever my delta is that particular less than epsilon by 2m delta naught, what I will get, I will have this difference has to be less than epsilon, and this will give continuity. So at then I have continuity of my function fxy, provided that I'm assume that my partial derivatives are bounded in a neighborhood. So finally we have finally we have the continuity of our function. So if I assume my partial derivatives to be continuous in a neighborhood, I will get the continuity. So with this, I will conclude my session. Thank you.